Hey students, we're going to go over the periodic table groups and families really quick here. So you may want to have your colored periodic table out that you did last week, so that way you can add some more information to it. In that notes page that was at the front of that paper, you might want to add some information to that as well. Okay, so first off, why are we looking at the periodic table? Well, the periodic table is a really useful tool for us. It has tons of information on it. It helps us to predict patterns and compare elements. It has our atomic numbers and our atomic masses that we're going to be using all throughout the year. So it's going to be really, really important for us to get to know this periodic table really well. Before the periodic table came around, everything was kind of a mess as far as the elements went. There was no organization whatsoever. It was very difficult to compare properties and everything amongst the elements because there was no way to visualize how they were all related to each other. And then came Dmitry Mendeleev, and he was the first one to actually come up with a format for the periodic table. So what Dmitry Mendeleev did was he was looking at the valence electrons and the way that these elements and atoms reacted with each other. He was also looking at similarities in physical properties as well, so that he could arrange them in a way that made sense. When he was arranging his periodic table, he put these elements in periods and groups, rows and columns. So the periods are what is going across and horizontally across the periodic table. And those periods, like we were talking about in electron configuration, correspond to the number of energy levels that you would find in that particular element. The groups and families are going to be the vertical columns. Those ones are based on similarities in chemical reactivity, and it's based on the numbers of valence electrons in those particular elements. Dmitry Mendeleev, what he did that was most impressive was that he left openings in his periodic table saying that there were elements that hadn't been discovered yet, that when they were discovered, they would fit right into these places that he left open on his periodic table. So he arranged his periodic table based on increasing atomic mass. That's not the case it is right now. For the most part, it's arranged by increasing atomic mass, but that's not how it's arranged. So he was looking at increasing atomic mass. He was looking at the way that these elements reacted, which is based off of their numbers of valence electrons, and he found patterns amongst these elements, and that allowed him to put elements that had similar valence electrons and similar reactivity in the same columns, and he was able to arrange them based on those increasing atomic masses. And then after Mendeleev's work with the periodic table, Henry Moseley came along and he just tweaked the periodic table a little bit, and he rearranged the elements so that they were based on increasing atomic numbers. So that's the number of protons that we have inside of the nucleus. There's a couple of places on your periodic table where you'll notice that the atomic mass is greater on the left and it's lower on the right. But for the most part, well, all of them are based on increasing atomic number. He just kind of rearranged a couple of the things that Dmitry Mendeleev did. So a little memory trick, we say Mos, pros, Mos for Moseley, pros for protons. When we're looking at the periodic table, I was talking about those periods and groups. So the periods are the rows on the periodic table. There's 7 periods. These lanthanides and actinide series fit right into rows 6 and 7 on the periodic table. We've just moved them down underneath the periodic table so that the periodic table doesn't stretch on forever, okay? So those 7 rows correspond to the 7 energy levels that you would see around the nucleus. Then we have groups or families. We call them both the same things. There are 18 groups or families. Those are your vertical columns. These have similar chemical reactivity, similar physical properties, and they have the same numbers of valence electrons. We have 3 main groups on the periodic table. We have metals, nonmetals, and metalloids. So you can see from this picture here that most of the elements are metals. All of these blue ones are metals. Those are the elements found to the left of that staircase zigzag line. The nonmetals, except for hydrogen up here on the top left, they are all to the right of the zigzag line. And then our metalloids are found right along the zigzag line here, except for aluminum, element number 13, that one's actually a metal. okay? So here's some characteristics of those three main groups: metals, nonmetals, and metalloids. And these are things that you've probably heard before from middle school or other science classes that you've had. I have added a couple of little things here, such as that metals are losers. That's right. Metals are losers. That means that they all lose their valence electrons when they are trying to get a stable electron configuration. All metals are losers. Nonmetals are called nonmetals because they're non-losers. They don't lose their electrons, they're going to gain electrons. And we're going to talk more about that as we go through these different groups. But all these other characteristics are things that you've probably heard before. Just remember, malleable means that it's able to be bent or shaped, and ductile means that it can form a wire. Metalloids, then obviously down here, say that they are going to have physical and chemical properties of both metals and nonmetals. So I put this here first, our noble gases, because it's something that we're all familiar with. Our noble gases are over here in group 18. And all of these, let me move this over here. All of these noble gases have the same ending electron configuration. They all end in P6, NP6, whatever that energy level is that they're in. And we know from prior science classes that noble gases are stable elements. That means they have a stable electron configuration. Not necessarily a full energy level, because we've discussed that before, but they have a stable electron configuration. 8 valence electrons is a stable amount. In all of the other elements, when they form bonds in order to get a stable electron configuration, okay? Now helium, because it's in the first energy level, only has 2 valence electrons, but all of your other noble gases have 8 valence electrons. And as we go throughout this, on the top of your columns, on your colored periodic table, you may want to put those ending electron configurations, so P6 for your noble gases, and you may want to put the numbers of valence electrons, 8 valence electrons. Now your noble gases are not going to form ions because for the most part, these do not form chemical bonds because they're already stable. If you would like to watch a little video about noble gases, you can click on this link in the top left. So then let's talk about alkali metals. So your alkali metals are going to be those elements in group 1 on the periodic table, except for hydrogen. Remember, hydrogen is a non-metal, so it is not an alkali metal. All of these alkali metals have an ending electron configuration of S1, okay? Just S1, 2S1 or 6S1 or whatever it is. They all end in S1. Now, these alkali metals are very, very reactive metals. They are very reactive metals. Because they only have 1 valence electron in the outer shell, and like I said before, all metals are losers. So they only have 1 electron to lose in order to become stable. That means that they are very reactive. They do react violently with water, so we do tend to keep those metals, those alkali metals, in some kind of submerged oil or something to help prevent them from reacting. And if you would like to see any of those reactions with water, you can click on one of these links up here in the top left. Alkaline earth metals, those are going to be your group 2 metals, beryllium to radium. And S2 is going to be our ending electron configuration. So if all of these have an ending electron configuration of S2, what does that mean about their valence electrons? Well, it means that they're going to have 2 valence electrons, just 2 valence electrons. So your alkaline earth metals aren't going to be as reactive as your alkali metals because they have to lose 2 electrons versus the alkali metals 1 electron. Okay. Your D block, which is groups 3 through 12, right here in the middle, those are going to be your transition metals. Okay, these are your transition metals. Now these electrons, or these atoms, excuse me, they are metals, they're going to lose electrons, but they can actually lose varying amounts of electrons, not just their valence electrons, because they have that D sublevel, which is really kind of funny compared to some of the other ones. So you can't easily tell how many valence electrons you have. If you have something such as, let me get my little text box here. If you have something like, manganese, for example, that has a 4s2, and then followed by a 3d5, you can see that from this ending electron configuration, these two electrons in the fourth energy level have are your valence electrons, so to speak, and the 3d5 go back and fill in inner energy level. So everything in the middle pretty much has two valence electrons, but that doesn't mean that they're only going to lose those two valence electrons. They could end up losing more or less than those two electrons when they're trying to become stable and get a stable electron configuration. And that's something that we're going to talk a lot more about when we get to our bonding unit. Okay? Oops. Our inner transition metals, these are our F blocks, our lanthanide and actinide series down here at the very bottom. A lot of these inner transition metals are radioactive, especially your actinide series. And again, the valence electrons are here, are difficult to say. For the most part, they have two valence electrons, but again, they can lose, because they're metals, so they're going to lose electrons, but they can lose different amounts of valence electrons in order to become stable. Okay, most of these are going to be man-made because they're so large. Here in this middle group here, groups 13 through 16, they tend not to fit into a regular family. Some of them are nonmetals, some of them are metals, and some of them are metalloids. But you can see the ending electron configurations for each of these. Just ignore the 2 in front because that 2 can change depending on if we're talking about boron or aluminum, for example, or if we're talking about carbon or tin. Okay, so it's really an NP1, NP2, NP3. Now you'll notice here that the valence electrons are not corresponding to the number of electrons in the P sublevel, because we have to remember that there are also valence electrons in the S sublevel. Boron, for example, has a 2s2 and then a 2p1, and those 2s electrons are valence as well as that 2p electron. Okay, so we need to make sure we're adding those S electrons into our P sublevel electrons to get our total valence electrons. So we have 3, 4, 5, 6 total valence electrons. Okay. Next, we have our halogens. Our halogens are group 17. Group 17. These are our most reactive nonmetals. So all of these have an ending electron configuration of P5. And remember, nonmetals are non-losers. So nonmetals are going to gain electrons. So remember, if the noble gases have an ending electron configuration of P6, then the halogens only have to gain 1 electron to become stable. So if they only have to gain 1 electron to become stable, that means that they are very, very reactive, very willing to attract an electron towards their nucleus so that they can become stable. So the halogens, they react very readily with your alkali metals because the alkali metals have 1 electron to lose and the halogens have 1 electron to gain. Those are called salts. We have different states of matter in our halogens, solids, liquids, and gases. If you would like to watch a video about the halogen reactivity, you can click on this link in the bottom right. So again, atoms are going to gain and lose electrons to get a stable electron configuration, meaning that they're going to try to gain and lose electrons to get the electron configuration of a noble gas ending in P6. So we can look at our valence electrons to help us to determine if an atom is going to gain electrons or if it's going to lose electrons. But we also want to keep in mind that all metals are losers. So all metals, regardless of how many valence electrons they have, are going to lose their electrons. And nonmetals are going to gain electrons. Okay? And here we've already talked about the valence electrons right here in the middle. But you're going to probably want to also record the charge of those ions on the top of your periodic table. So we've talked about this already, about how the alkali metals have 1 valence electron and they're going to lose it, which is why they have a +1 or will form a +1 charge. The alkaline earth metals have 2 valence electrons that they're going to lose when they become stable, so they will form a positive 2 charge. Whereas your halogens, for example, have 7 valence electrons. They're going to gain just 1 electron because it's a nonmetal, and that's why they form a negative 1 charge. Remember, electrons are negative, which indicates if that charge is going to be positive or negative. We have 2 terms down here at the bottom, anion and cation. An anion is a negative ion. So all of our nonmetals are going to form negative ions when they lose their electrons, because they're all going to form negative ions. Sorry, when they gain electrons, they're going to form anions because they're all going to gain electrons to get that stable electron configuration. Your metals are losers, and your metals are going to form cations, which are positive ions, because they all become positive when they lose electrons because they have more protons than electrons. So make sure you know those terms, anions and cations. They are going to become very important when we get to our ionic compound unit. So when we write electron configurations for ions, we were writing electron configurations in our last unit. Let me erase my circle here. But we kind of glossed over the ion portion of it. So when you're writing your electron configuration, first off, you're going to want to figure out how many electrons a neutral atom is going to have. And then you need to add or subtract electrons from that neutral atom to determine how many electrons the ion is going to have. Once you determine how many electrons the ion is going to have, then you can write the electron configuration for the new number of electrons. So what does that look like? I thought I had it in here. Let me add a text box. So that's going to look like if we, for example, had nitrogen with a -3 charge. Nitrogen, as we know, has 7 electrons. And -3 means that it gained 3 electrons, and now it has 10 electrons. So we would basically be writing the electron configuration for neon. So we would have 1s2, then we'd have 2s2, then we have 2p6, totaling 10 valence electrons. If we had magnesium 2+, sorry, I can't do superscript here. If we have magnesium 2+, that 2+ means that magnesium lost 2 electrons. So magnesium typically has, as a neutral atom, 12 electrons. So if the ion loses 2 electrons, now it has 10 electrons, meaning its electron configuration is going to be the same as neon as well. So the nitrogen ion and the magnesium ion would both have the same electron configuration as neon, because those 2 ions would have 10 electrons total. Okay, so again, let's say we're going to do sulfur -2, and we want to make sure we're going to write the ions electron configuration. So sulfur has, as a neutral atom, 16 electrons. So if it gains 2 electrons, it has a -2 charge, it's going to have 18 electrons. So now, instead of writing the electron configuration for sulfur, we're going to write the electron configuration for argon. And we would have 1s2, 2s2, 2p6, 3s2, and then 3p6. Okay? So that's it. If you have any questions, let me know, and go ahead and practice on pages 2 and 3 in your packets. Okay? See y'all later.